Hello, dear grade 12 students. Hope you are all doing well. I'm Mr. Idris. I'm back again with a new lesson. In a previous lesson, if you remember, we have talked about the moment of inertia. Moment of inertia, we can define the moment of inertia as the resist of the change in rotational motion. Okay, if you remember, we have many different shapes that has its own moment of inertia, such as a solid sphere. Its moment of inertia is equal to 2 over 5 mr square, and the hollow sphere, such as a basketball, its moment of inertia 2 over 3 mr square, and the solid disc, such as a merry-go coin, its moment of inertia is equal to 1 over 2 mr square, and for the thin hoop and the ring, its moment of inertia is equal to mr square. And we solved all the questions which is related with the moment of inertia, okay? But on today's lesson, we're going to explain the two conditions of equilibrium, okay? If you remember in grade 11, you have learned about the translational equilibrium. When does an object to be in a translational equilibrium? In two cases, if the object at rest or if the object is moving with a constant velocity. In these two cases, the object considered to be a translational equilibrium, okay? But in this chapter, so you will learn about the rotational equilibrium also, okay? For an object to be completely in equilibrium, both rotational and translational, there must be both zero net force and zero net torque, okay? So this is called the two conditions of equilibrium, okay? So how many conditions of equilibrium do we have? We have two conditions of equilibrium: rotational equilibrium and translational equilibrium, okay? I'm sorry. Okay. Equilibrium. How many conditions of equilibrium do we have? Two. Translational equilibrium. Let's change color. Translational equilibrium, and the second condition is rotational equilibrium. Okay? In translational equilibrium, when does an object to be in a translational equilibrium? In two cases. When object at rest okay, but before explaining this, be sure that the translational equilibrium, in translational equilibrium, net force is equal to what? Zero. Net force is equal to what? Is zero. When does net force equal to zero for an object? In two cases. When object at rest, okay, why? Because when the object at rest, V initial, zero. V final, zero, because the object at rest, okay? So delta V also zero, okay? Zero. When delta V change in velocity is zero, acceleration also zero. Why? Because acceleration is what? Change V final minus V initial over time. In the case when V final is equal to V initial, acceleration becomes zero, okay? When acceleration is zero, according to Newton's second law, Newton's second law says mass time is equal to mass times acceleration, okay? Newton's second law, net force is equal to what? Mass times what? Times acceleration. When acceleration is equal to zero, what happens to the net force? Net force also zero. So if the object is at rest, place it at the rest. In that case, the object, we can say the object has translational equilibrium, okay? The second one, in the second case for the translational equilibrium, so when does an object has translational equilibrium? If the object is moving, when object is moving with constant velocity. What do you mean by constant velocity? It means that V initial is not equal to 0. It is equal to something, okay? V initial is equal to V final. In that case, if V initial is equal to V final, delta V is equal to what? 0. If delta V is equal to 0, acceleration, it depends on the change in velocity. If there is no change in velocity, there is no acceleration. Acceleration also 0. If the acceleration is 0 according Newton's second law, which is equal to mass times acceleration, net force also equal to 0. Okay, so finally we can say the object has translational equilibrium if net force equal to 0. When does net force is equal to 0 of an object? If the object at rest or if the object is moving with constant velocity. Okay, this is all about the translational equilibrium. For rotational equilibrium, okay, for rotational equilibrium, so the object becomes the rotational equilibrium of the object has rotational equilibrium in two cases. When object doesn't rotate, it means that there is no rotation. No rotation. In the case of no rotation, it means that omega initial 0. Omega final also 0. Okay? So what about change in angular speed? Also 0. If the change in angular speed is equal to 0, angular acceleration also becomes 0. Why? Because angular acceleration depends on what? Angular acceleration depends on the change in angular speed. Okay? So that is why angular acceleration also 0 when delta omega 0. Why? Because angular acceleration is equal to omega final minus omega initial over time. If omega final is equal to omega initial, okay, or both are 0, angular acceleration also becomes 0. Okay? When alpha is 0, according Newton's second law for rotational motion, okay, torque is equal to I alpha. What is this? This is Newton's second law for rotational motion. Okay? If alpha is equal to 0, what happened to the net torque? Net torque is equal to 0 also. Okay? So for rotational equilibrium, net torque must be 0. Okay? 0. Okay? Net torque is equal to what? 0. But in translational equilibrium, net force is equal to 0. Okay? What is the condition of rotational equilibrium? Net torque equal to 0. When does net torque equal to 0? If the object doesn't rotate or in the case of no rotation. Okay? The second case in rotational equilibrium, when an object rotates with constant angular speed. When an object rotates with a constant angular speed, such as a ceiling fan, for example, when the ceiling fan is rotating with constant angular speed, it is rotating, okay, but with constant angular speed. There is no acceleration, there is no deceleration, there is no angular acceleration, okay, in that case. So, if the angular speed is constant, it means that omega initial is equal to omega final. Okay? This is not 0, be careful. Omega initial is equal to something, for example. If the ceiling fan is rotating or the merry-go is rotating with a constant angular speed, it means that omega initial, for example, assume that 5 radian per second. It is omega final also 5 radian per second. They have the same angular speed. In that case, alpha is equal to what? Alpha is equal to 0. Why? Because in the case when omega initial is equal to omega final, delta omega also is equal to 0. When delta omega change in angular speed is equal to 0, what happened to the alpha? Also alpha is equal to 0. According to this equation, net torque is equal to what? I alpha. If alpha is equal to 0, net torque also equal to 0. This is the two conditions of equilibrium. It is very important. I'm going to review, please. We have two conditions of equilibrium: translational equilibrium and rotational equilibrium. When does an object has translational equilibrium and when does an object has rotational equilibrium? In the case when the object at rest, there is no movement, V initial, V final, both are equal to 0. In that case, delta V also equal to 0. According to Newton's second law, net force, acceleration and net force becomes 0. Okay? And when an object is moving, also it's going to be a translational equilibrium, but with a constant velocity. When the object is moving with constant velocity, there is no acceleration on the object. If there is no acceleration, it means that there is no net force on the object, and net force is equal to 0. This is the translational equilibrium. Rotational equilibrium, in rotational equilibrium, net torque, it should be equal to 0. When does net torque is equal to 0? When object has no rotation, or when object is rotating with constant angular speed. Okay? Okay, guys, listen carefully, please. Now, we're going to solve some questions related with the two conditions of equilibrium. Okay. As you can see here, okay, this is the two conditions of equilibrium: translation and rotation. Okay. We have some questions, some wizard questions. Listen carefully, please. In which of the following case the object has rotational equilibrium? Has what? Rotational equilibrium. In the rotational equilibrium, omega is constant? Yes, of course. If omega is constant, the object has rotational equilibrium? Yes. In the rotational equilibrium, the summation of torque or net torque acting on the object also equal to 0? Yes. This is right, okay? Angular acceleration is equal to 0? Yes, of course. So D, all of the are true. Okay, all answers are true. Okay. The second question: which of the following correct one object to be completely in equilibrium? When we say completely equilibrium, it means that the object has both translational equilibrium and rotational equilibrium. Because sometimes some object has only translational equilibrium, not rotational equilibrium. Sometimes some object has rotational equilibrium, not translational equilibrium. And sometimes we have an object has both rotational equilibrium and translational equilibrium, and sometimes the object has neither rotational nor translational equilibrium. Look at this question. Very good question. Be careful, please. Pay attention. Which of the following correct one object to be completely in equilibrium? Only net torque equal to 0? No. Only net force equal to 0? No. Net torque is not equal to 0. Net torque is not equal. No, this is not correct. D is correct. For the object to be a completely equilibrium, it should be both net force and net torque equal to 0. Okay? Which of the following is correct if one object that is not in a rotational and translational equilibrium? Both net torque and net force is not equal to 0. In that case, the object has neither translation and rotational equilibrium. In which of the following case the object has translational equilibrium? Translational equilibrium. In translational equilibrium, V should be constant. V constant is right? Yes, of course. Net force 0? Yes. Acceleration 0? Yes. All of them. Okay? Question 12, chapter review. Look at this question. What are the conditions for equilibrium? The conditions of equilibrium, it is at the both conditions. The conditions of equilibrium: net force 0 and net torque 0. 0 net torque, 0 net force. This is the conditions of rotational and translational equilibrium. Explain how they apply to children attempting to balance a seesaw. Okay. Each child must be equal and opposite. Okay, how can you apply these two conditions of equilibrium to the seesaw? Okay, assume that this is seesaw. Okay, and this is apply the children to balance the seesaw. This is a pillar. Okay, we have two child sitting in each end, okay? Okay? So, the force of the seesaw exerted by this pillar is upward force. What is this? This is the force of the pillar on the seesaw, okay? And these two forces, this is the gravitational force for the first child and this is the gravitational force for the second child. If this seesaw is in the balance, we can say both net force 0, net torque 0. There is no rotation, there is no up and down. The seesaw is in the balance. Okay? Can we balance two objects? Of course. If they are equal mass, or for the different masses, we can balancing this seesaw by moving the heavier object of the child near the axis of rotation. Okay? In that case, the seesaw is in balance. But the force exerted by the pillar, or pivot, it should be equal. Equal what? The two forces of the children, Fg1 plus Fg2. Okay? So in that case, these two forces are in opposite direction. Okay? If you add up these two forces, we can get that net force is equal to what? 0. Okay? Assume that this is 100 Newton. This is 15 Newton and this is 15 Newton. 15 plus 50, 100. 100 minus 100 equal to 0. Net force on these two children and the seesaw is equal to 0. Okay? This is about the, so we can say this seesaw has translational equilibrium. For rotational equilibrium, look. Okay, how many gravitational forces do we have? We have two gravitational force, two downward gravitational forces. Sorry. Okay, this is axis of rotation. What is this? This is axis of rotation. Okay, if we move away this child, what happens to this? This is Fg2, Fg1. Okay, if you remove this child, what happens to the seesaw? The seesaw try rotating. In which direction? Clockwise direction. Okay, if you remove this child here, what happened to the seesaw? The seesaw cannot be in the balancing anymore, so instead it is rotating clockwise. Okay, so it means that torque number 2, it becomes what? It becomes negative. Okay, but in the case when you remove this children, the second children, what happened to the seesaw? The seesaw cannot be in the balancing anymore, it is rotating. How? Counterclockwise. Okay. Counterclockwise. Torque number 1 becomes positive. How many torques do we have? Now we have two torque. Two torque with the same magnitude but opposite direction. If you have two torque with the same magnitude but in opposite direction, net torque is equal to what? Is equal to 0. Can we say this seesaw has rotational equilibrium and translational equilibrium? Yes, of course. Because both net force, upward force and downward force are equal but opposite direction, and both torques, torque number 1, torque number 2 for these two children are equal in magnitude but opposite in direction. Okay? Yeah, so the answer is the force of the seesaw support must equal the children's net weight and the torque exerted by each child must be equal and opposite. This is about the question 12. Chapter review, okay? The two forces acting on the table are equal in magnitude and opposite in direction. However, the table moves. How it happens? Yeah, this is F1 acting on this point, okay? And this is F2 acting on this point, okay? What happened to this table? The table starts rotating. Maybe net force is equal to 0 if the two forces are equal in opposite direction. Net force is equal to 0, but we cannot say net torque equal to 0. Why? Because the object has the net torque is not equal to 0 when it starts rotating. In the case of speeding up, okay? The table rotates to the net force acting on the table is 0, but net torque is not equal to 0. Okay? If an object is at rest,
Can you be certain that no external torque are acting on it? No. For example, when the table is rotating at its position without velocity, without moving, okay? So in that case, there is torque, but the two torque, if an object is at rest, can we certain the net external torque are? No, never. The torque is maybe in equilibrium. Okay? If omega is constant, when the object rotates with the constant angular speed, alpha 0 and net torque is also equal to 0. Okay? Question 16 in chapter review. Is it possible to balance two objects that have different mass, irregular shape, okay, and therefore weights on a single balance beam? Yes, of course. For example, if you have a seesaw, this is pivot or a pillar, okay? This is axis of rotation, okay? If you have two child on the seesaw, okay? If G1 is equal to, for example, 400 Newton, if G2, for example, is equal to 800 Newton, okay? The child with the 400 Newton should be placed here, okay? This is FG1 with the 400 Newton. The second one, because this child is heavier than this child, because it has more weight, you have to place this child here. Okay, Fg2 is equal to 800 Newton. So in that case, the seesaw becomes balancing and there is no rotation, there is no net force. In that case, the object of the seesaw can be in a completely equilibrium. Okay, by how can we balancing two different masses? How many masses do you have? Two different masses. Can we balancing the two different masses on the seesaw? Yes, of course. By moving the heavier mass near the axis of rotation. Near what? The axis of rotation. And also you can say by moving the lighter mass away from the axis of rotation. This is axis of rotation. How can you balancing two different masses on the seesaw? By moving the heavier mass near the axis of rotation, or by moving the lighter mass away from the axis of rotation. In these two ways we can balancing the seesaw or any object. Okay? Okay, guys. So yes, by moving the less massive object farther from the axis of rotation. So we have some notes for solving the questions which is related with the rotational and translational equilibrium. Okay. The forces on the axis of rotating has zero torque because the distance from the axis of rotation is zero. When the mass is given, gravitational force is equal to mass times gravity. If the balancing point is in the center, located at the middle, you have to equalize all torques to the right with all torques to the left, and all forces to the right with all forces to the left. When the axis of rotation is located at the middle, okay? Such as a seesaw. When the axis of rotation is located at the middle, you have to use that net force equal to 0. The force acting to the right is equal to the force acting to the left. Okay? And vice versa is true. Force to the left equal to force to the right is the same because this is 0. For the net torque, rotational equilibrium, if the axis of rotation located at the middle, such as a seesaw, in that case, if net torque is equal to 0, all torque is acting to the right is equal to all torque is acting to the left. But all the torques and forces on the upper and lower sides of the object must be equal if the balancing point is at one end. But for example, if the balancing point is located at one end, okay, for example, if you have FT1, and FG and FB, okay, in that case you have, because the axis of rotation is located at the end, you have to say all upward force is equal to all downward force. Why? Because the axis of rotation is located at the end, and all upward torque is equal to all downward torque. We have only one upward torque and two downward torques. Okay? If the question asks for a single force, one force, if the question asks us to find only one force, because sometimes two forces are unknown. But in the case when one force is unknown, only you have to use the rotational equilibrium without using translational equilibrium. Okay? You have to use what? The rotational equilibrium only. Because sometimes for some questions we have to use both rotational equilibrium and translational equilibrium. When does only rotational equilibrium can be used? If the questions ask us to find only one force. But when two forces are unknown in the question, in that case you have to use both types of equilibrium. Rotational equilibrium and translational equilibrium. Okay? Only single forms of specific distance or a distance also the same thing. We will only satisfy or use or apply the condition of rotational equilibrium. But if two forces are unknown, you have to use both. Okay? If the force is an angle, sometimes the force makes an angle with the horizontal or vertical. For any force, when it makes an angle, you have to divide or solve this force into two components. Be careful, okay? So in that case, you have to find the x component and the y component of the force. Okay, so the rotation axis is chosen arbitrarily because you can select the axis of rotation. Because sometimes in some questions, they do not give you the axis of rotation in the question. So without the axis of rotation, you cannot solve the question. Be careful. In that case, how can you choose or select the axis of rotation if it's not given in the question? It's up to you. Okay? So, for example, if the scaffold or beam is supported by two cables, okay, the position of these two cables can be the axis of rotation. So you can make one of this end as an axis of rotation. Okay? I'm going to explain in detail when we are solving the question. Okay? So the rotation axis is arbitrary because the requirement for rotational balance is an effective by however trying to select the point where the torque is 0 to rotational equilibrium, which is d is equal to 0. So we can balance the object different ways, I told you, okay? Now, rotational and translational equilibrium. About the rotational and translational equilibrium, before we start solving the questions, I would like to tell you some good information about the rotation and translational equilibrium because it's very important. For the rolling object, guys, be careful. When we say rolling object, it means that the object is rolling. When the object is rolling, the types of motion is rotational and translational. Why? When the ball is rotating, it has rotational motion. When the ball changes position, it has translational motion. Okay? So in that case, for rolling object, if the object is rolling with a constant velocity, listen carefully please. If the object is rolling or moving with constant velocity, if V initial is equal to V final, in that case, acceleration 0 and net force 0. The object has translational equilibrium. When V initial is equal to V final, also omega initial is equal to omega. Such as a bicycle. When the bicycle is moving with constant velocity, its angular speed also is constant. It's impossible for the bicycle or for the car, it's moving, its velocity is bigger than angular speed. It can never be happen. Careful. When the bicycle is moving with a constant velocity, it means that this bicycle also has constant angular speed. Okay? When velocity is constant, it is net force equal to 0, it has translational equilibrium. When the bicycle is moving with a constant velocity, it has also constant angular speed, which is required for the rotational equilibrium. Okay? For rolling objects such as a rolling bowling ball or wheels or bikes, cars, this type of motion has both translation and rotation. Okay? So in this case, if velocity is 0, omega also 0. Or constant speed, when the object or bicycle is moving with constant, it has both rotation and translational equilibrium. Okay? So, if the question asks you, when the bicycle is moving with a constant speed, which type of equilibrium do they have? The bicycle has both rotational equilibrium and translational equilibrium. Why? Because its velocity is constant. Also, its angular speed is constant. Okay? But if the velocity of the bicycle changes, speeding up or slowing down, When the bicycle speed changes, what happens to the angular speed of the tire? Also changes, because it is directly proportional. Okay? V is equal to what? Omega R. When V increases, omega also increases. When angular speed increases, the velocity also increases. They are changes together. So if the bicycle is speeding up or slowing down, it has major rotational and translational equilibrium, because net force not equal to zero, net force not equal to zero. Okay? The second case, this is for an object that has both types of motion. Okay? Guys, when we say for rolling object, it means that the bowling ball or the bicycle is rolling on a surface. Okay? The type of this motion has both translational motion, because its position changes, and rotational motion. Okay? So in that case, if the object is moving with a constant velocity, okay, or when object is at rest, V0, delta V0, omega 0. When delta V0, net force also 0, net torque also 0. Okay? Or when object is moving with a constant speed. Okay? If the object is moving with a constant velocity, V initial is equal to V final. This is the condition of translational equilibrium. Net force 0. And also omega initial is equal to omega final, which is the condition for rotational equilibrium. Okay? But if the velocity changes, if V initial is not equal to V final, omega initial also is not equal to omega final for the bicycle, for the bowling ball, or bike, or any other motion. Okay? So in that case, if V initial is not equal to V final, acceleration is not equal to 0. Net force is not going to be 0. Okay? So the object has no translational equilibrium in the case of speeding up or slowing down. When we say V initial is not equal to V final, it means that this object has speeding up or slowing down. Okay? Because in the two cases, the velocity changes. If velocity is not equal, also angular speed is not equal. Okay? So alpha is not equal to 0 because the object has angular, it has the change in angular speed. And also net torque is equal to 0. Okay? This object has both types of translation and rotational motion. Translational motion and rotational motion. The second type for rotating object only. Such as the selling fund. Okay? The selling fund. Okay? Let's draw the selling fund. Okay? Okay. The selling fund is fixed. The velocity of the selling fund is equal to what? 0. V initial 0. V final 0, because the selling fund is fixed at its position. If this position doesn't change, it means that the selling fund has no velocity. Be careful, okay? If the selling fund has no velocity, delta V also equal to 0. And net acceleration equal to 0. Net force equal to what? 0. So we can say that when the selling fund is rotating or doesn't rotating, in both cases, in the case of speeding up, slowing down, more angular speed, less angular speed, in all cases, the selling fund or the object that has only rotating or rotational motion, we can say this object has translational equilibrium. For rotating objects only, for rotating objects such as a ceiling fan or merry-go, it is fixed at its position. This is not like a bicycle. The bicycle can change position, but the ceiling fan cannot change its position. Its velocity is zero. So that is why the ceiling fan or the object that's rotating only they have the rotational motion, the object we can say always to be at translational equilibrium. But for rotational equilibrium, if omega is equal to omega initial is equal to omega final, when the ceiling fan has constant angular speed, only in that case net torque is equal to 0. But if omega initial of the ceiling fan is not equal to omega final, so in that case net torque is not equal to 0. Okay? So let me ask you a question. Listen carefully, please. If the ceiling fan is start rotating, okay, or the ceiling fan's angular speed increases. Look, the ceiling fan's angular speed increases. Which type of equilibrium does the ceiling fan has? You have to say only translational equilibrium. Why? Because you have to say, teacher, the ceiling fan has no velocity, so that is why it has translational equilibrium. And you say the angular speed increases for the ceiling fan. When the angular speed increases, it means that angular speed is not constant. Omega initial is not is equal to omega final. So in that case, net torque can never be 0. So the ceiling fan finally we can say has translational equilibrium but not rotational equilibrium. Another question. If the ceiling fan is rotating with a constant angular speed, which type of which condition of equilibrium does the ceiling fan has? You have to say both. Because the ceiling fan has zero velocity, has translational equilibrium, and because you say the ceiling fan has constant angular speed, in the case of constant angular speed also has rotational equilibrium. So we can say both rotational equilibrium and translational equilibrium. The third one for moving object without rotating, or you can say dropping object. Dropping object. In that case, when the object is moving without rotational motion, such as, look at this incline. If you have a box here, this is box. If you release this box from this incline right up into the box, it's moving downward. Do we have rotation? No. The object has no angular speed. For moving object only without rotating, the object's angular speed is equal to what? 0, 0, or you can say delta omega 0 and alpha 0. Net torque always equal to 0. For dropping object or for moving object without rotation, can you say this object has always rotational equilibrium? Yes, of course. The object is in a rotational equilibrium. But if the object is moving with a direct speed, okay, such as dropping ball, okay, we cannot say this object has translational equilibrium, okay. But if the object is moving with a constant velocity, V initial is equal to V final, in that case acceleration 0, net force 0, translational equilibrium. But if V initial is not equal to V final, acceleration is not equal to 0, net force is not equal to 0. Let me ask you a question. If the box or ice cube is moving with constant velocity, which type of equilibrium do we have for this object? We have both types of equilibrium. Because the box isn't rotating, it has rotational equilibrium, and because the box is moving with constant velocity, has translational equilibrium. Another question. If you drop a ball, drop, not rolling, be careful, drop. When we say drop, it means that the ball is not rotating. If you drop a ball at some height, So can we say this ball has both types of equilibrium? No. Because the ball is dropping, has no rotation. Yes, it has rotational equilibrium. But the ball has no translational equilibrium. Why? Because when we release the ball at some height, what happens to the velocity increases due to the gravity. Because the velocity changes, so we cannot say this ball has translational equilibrium. So in that case, for dropping ball, the object has only rotational equilibrium, not translational equilibrium. Look at these questions. A bicycle tire on a flat road rolls at a constant angular speed, and the bicycle has. But before solving these questions, I would like to correct some. There is some mistake here. If velocity changes, omega changes, it has neither rotational equilibrium. But for rotating object only, such as a silicon merry-go-round and turntable, this type of motion has only rotational motion, and always it has translational equilibrium. If it is velocity 0, which means that it has translational equilibrium. If omega is constant, it has both translation and rotational equilibrium. But if omega changes, it has, okay, delete this please, this is wrong, this is mistake, okay? So you can remove this. Instead, write down this. If omega changes for rotating object, net force also equal to 0. That net force not equal to 0. Just write down here, okay? Remove this, okay? Delete this and write down here. For the moving object only also, if velocity changes, this is wrong, okay? Remove this please. If velocity changes, net force is not equal to 0, has no translational equilibrium, but has rotational equilibrium. Okay? Opposite of this one. Please correct this because I mistaken, sorry. Okay? Remove these two sentences and instead write down this, okay? Some questions about the rotational equilibrium and translational equilibrium. Look at the questions. Okay, guys. Inshallah, in the next lesson, we are going to solve the questions, and inshallah, we will finish section 2 and we start explaining section 3, chapter 2. We are all doing well, and thank you for listening.